I usually start off my videos by talking about a physics or engineering topic that's related to the thing that I'm planning to build. However, I've been working on this project for about 8 weeks now and it's not going to work. This is pretty much the full extent of what I've built. As you can probably see, it doesn't resemble anything that you've just read in the title of this video. So I think what I'm going to do is I'm going to show you everything I've been developing, and hopefully we can piece together some of these parts to produce something that kind of does something.
This video is sponsored by Kiwico. More about them later. For a helicopter to fly, there are 3 main requirements. The first is it must produce enough thrust to lift its own weight. The second is it must have some form of stability or control to keep itself level and prevent a crash. And the third is all the torque produced by the rotor must be counteracted either with a tail rotor or another rotor that spins in the opposite direction. After reading the comments on the previous air turbine video, several of you suggested I should build an air-powered quadcopter. And I agree, 4 turbines attached in a cross formation all controlled by compressed air will be awesome. For a drone to sustain smooth, stable flight, it's very important that the propeller and motor specifications are matched for their intended RPM. For example, this tiny motor is designed to spin at 30,000 RPM, but this large propeller is designed to spin at just 5,000 RPM. So it would be like trying to put tractor wheels on a Formula 1 car. But aside from the thrust produced, a quadcopter is controlled by varying the speed of its propellers. And generally smaller propellers have less rotational inertia, which means they require less torque to change speed. And since the turbine I've designed doesn't have much torque, I'll need some smaller propellers. This means adjusting the turbine gear ratio to match the optimum RPM of the smaller propeller. The only problem is I can't get it to produce anywhere near the amount of thrust of the larger propeller, which I can only narrow down to the smaller propeller being less efficient. I then mounted an electric motor on the thrust test stand to spin the propeller at a controlled RPM, which allowed me to measure the power being drawn from a battery. This is essentially a basic method to measure the propeller efficiency. By slowly increasing the motor RPM, I can log the power consumption and the thrust produced to plot a thrust versus power graph. And from this we can read the efficiency of the propeller. For example, at 10 watts of power consumption, this propeller produces 1.16 newtons of thrust, or equivalent to lifting 118 grams. I then repeated this test with the larger propeller, and the results were very clear. For the same power output, the larger propeller produces nearly 40% more thrust, which is a huge difference in efficiency when we're searching for small 5 to 10% improvements in the turbine design.
So this is where the problems begin. The larger propeller is so much more efficient than the smaller propeller that I basically have no other choice but to go with the larger one. But using this on a quadcopter will be difficult to control, as well as the frame will need to be large enough so the blades don't overlap, meaning it will weigh more. So I think what we need to do is go back to square one and go with a helicopter design. The only thing we need to worry about with the helicopter design is that because it only has a single large rotor, it needs to have a tail rotor to counteract the torque produced by the main rotor. And because the tail rotor pretty much only blows air sideways, it's basically consuming the compressed air that we need to use as the helicopter's fuel, but it's not producing any useful thrust to lift the helicopter off the ground. But what about a helicopter with contra-rotating blades like the new Mars helicopter, where both blades spin in opposite directions? This would counteract any rotor torque, but would also mean we need to build a gearbox and shaft system so that each propeller could spin in opposite directions, which isn't a problem for an electric aircraft, but because these air turbines can't produce much thrust, it's probably going to produce too much friction with the gearbox and also a lot of weight. The other option is to mount a turbine on top and another turbine underneath the craft, as this will basically achieve the same thing of the torques being counteracted, but we won't need a complex gearbox and shaft system. But there is another issue. 2 turbines means added weight and also twice the air consumption. So we just add more compressed air bottles, right? Well, this starts to spiral into a vicious circle of needing more thrust, and then to produce more thrust we then need more compressed air storage, which then adds more weight, and then we need more thrust again to lift that extra weight, and so on. And if we look back on the propeller efficiency graph, at low thrust values, it produces about 20 grams of thrust per watt. But at higher thrust values, it only produces 13 grams of thrust per watt. So as the thrust is increased, the propeller efficiency decreases, probably due to extra drag of the propeller having to spin faster. So what we need to do is produce the lightest possible craft that we can with a single turbine and a single plastic bottle.
Something interesting I realised whilst considering a tail rotor is instead of mounting a turbine to the end of a tail boom, why don't we use a small nozzle to bleed off some compressed air? Since torque is the product of a force at a perpendicular distance, if we have a really long tail boom, it will only require a small amount of thrust to keep the helicopter pointing straight. Let's take for example, one of the turbines is mounted on a 0.2 meter long tail boom. It produces about 1.4 newtons of thrust at 4 bar of pressure, which means a torque of 0.28 newton meters is produced, with a total weight of 58 grams. Whereas if we take that same nozzle from the turbine, mount it on the end of a 0.8 meter tail boom, it produces far less thrust, but we get the same torque produced whilst consuming the same quantity of air, but it now weighs just 27 grams, which is a huge difference. I then came across a YouTube channel called Science-ish, and he made a video where he produced supersonic shock diamonds by burning alcohol inside of a plastic bottle. And guess what? I'm also using a plastic bottle, which could suggest my nozzles are producing shock diamonds too.
To see if these nozzles are actually producing supersonic flow, I've decided to build what's called a schlieren imaging setup. Essentially there's a magnifying glass lens right here. Lots of people would like to use mirrors from telescopes, but I couldn't find any for a reasonable price, so I picked up this magnifying glass lens off Amazon for pretty cheap. And at the focal distance of this lens is a small point of light. It's basically an LED mounted inside of a 3D printed housing. Now at the other end of the focal point of this lens is a camera, and positioned just in front of the camera is a very sharp blade. And the idea of this setup is that over this long distance, air is going to refract any kind of light that travels through it. So basically if you have a high density portion of air or a low density portion of air, it will either be refracted up or refracted down. So some of the stuff that is either high density or low density will hit the knife and will cause a shadow in the camera image. It's probably better if I give you a quick demo with a candle lighter. Okay, so the high-speed camera is recording, so I should just be able to light the candle in front of it, stop the high-speed camera, and then if we take a look at this, should be able to see some pretty cool airflows coming out of that. That's so cool. So I've now got the nozzle mounted in front of the lens, and I've got a pressurized bottle down here. It's not actually pressurized yet, but I'm just about to pump it up, and then we'll see whether we're actually getting supersonic flow. We go to play, and is there anything there?
Unfortunately, the resolution of my high-speed camera isn't great, and it was also slightly out of focus. So I ran the test again using my stills camera and captured this awesome shot, where the shock diamonds are clearly visible. But what does this mean? Well, maybe I can design a bell-shaped De Laval nozzle, like you see on rocket engines. Now, I have no idea about that area of fluid dynamics, but fortunately the clever folks over on Twitter saved me a lot of experimentation. Though I still had to test the theory. So I printed 2 more nozzles with a very small expansion section, and there is definitely a visible difference in the schlieren imaging. However, the theory was correct. The simple standard nozzle produced the most thrust. In the spirit of keeping it simple, I attached the turbine directly to a carbon fibre tail boom, and because the tail boom is hollow, if I seal off both ends it can be pressurised. At the turbine end of the tube, I designed a 3-way fitting that allows the incoming air to pressurise the tail boom, but also acts as a nozzle to power the turbine. Then at the other end of the tube, I can mount a 90-degree nozzle which will act as a tail rotor. With the propeller and air supply attached, I can spin the turbine and see how the torque compensation works. And it seems to be working better than I expected, so I need to reduce the diameter of the tail nozzle. But at least it seems to have enough thrust. I then printed a very basic rotor head, which was inspired by Peter Schreipel's rubber band helicopter, where the blades are just attached to a pivot, and then a weighted stabiliser bar is attached at an offset angle. This stabiliser bar is very common on small scale helicopters, and the idea is that the gyroscopic stability of the bar will keep the helicopter level during flight, or at least long enough for the air supply to run out. So with the helicopter suspended from a bearing mounted string, it's time to see if this thing is going to fly. Aside from the air supply tube pulling the helicopter around, it's actually looking a little promising. So let's attach a one-way inlet valve to fill the bottle and see if it can run on its own air. And without the safety tether? It seems the nose of the helicopter pitches up very violently as soon as it takes off, which throws the stabiliser bar way out because it's only restricted to about 30 degrees of tilt. I think the reason for this is the air supply acts as a nozzle once the helicopter lifts off, producing a fast jet of upwards moving air, which hits the helicopter nose. I also noticed the turbine barely runs for more than a couple seconds, almost like the propeller blades are just freewheeling, which suggests the bottle isn't being pressurised. To fix both these issues, I redesigned the inlet nozzle with a larger diameter, so there is more airflow into the bottle than there is exiting via the turbine. I also designed the nozzle to vent air sideways once inside of the valve, so when the helicopter takes off, there isn't a vertical stream of air pushing upwards on the nose. The only problem is the new large diameter inlet nozzle has too much friction for the thrust of the helicopter to overcome. So why not give it a little help? For one final attempt to see this thing soar into the air, I built a small lever to assist it off of the nozzle. The bottle definitely seems to store more pressure now as the turbine spins for a lot longer. So let's remove the safety tether one last time. Just a little more pressure should do the job. I'm going to pause right here and show you the slow-mo instead, because not only does everything look better in slow-mo, but it also makes the flight time seem longer.
Honestly don't know what else to try with this project. I just don't think it's going to work. But you know what does work? kiwico crates.
kiwico create these awesome crates that each contain hands-on projects that are designed to expose kids to science, technology, engineering, art and math, and they never fail to impress me. The crates are designed by experts to not only be educational but also great fun, and each box includes all the required supplies, so there's no need to go to the hardware store, as well as a clearly laid out, kid-friendly instruction manual. Every kiwico crate is different, and there's over 8 different subscription lines, each catering to different age groups and topics, so there's something new to learn every month. kiwico believes that the best way to change our world tomorrow is to teach kids the skills of problem solving and innovation today. And I completely agree. Learning how to problem solve really opens up future ideas and opportunities. I just wish I could improve my table tennis skills.
You can get 50% off your first month of any kiwico crate by going to kiwico.com/Tom50. The link will be down in the description below. Thank you to kiwico for sponsoring this video, and thank you very much for watching. If you enjoyed this video, it'd be great if you could leave a thumbs up down below. If you're new to my channel and want to see other projects like this, then please click subscribe down below. And a massive thank you to all of my supporters over on patreon.com for making this project possible. I honestly couldn't build these kind of things without your support. So thanks once again for watching, and I'll see you in the next video. Goodbye.